Good evening, everyone. Okay, so today I'm going to finish up both parts E and F of in-class exercise number 7, which has been left over from last class, right? And then, if time allows, I will give you another in-class exercise problems, okay? Okay, this is the LP problem that we have been working on, and we've already answered for the first 4 questions, A, B, C, D, right? And now we are required to solve this problem using big M method, right? And after that, we're going to implement two-phase method to solve this problem. Okay, so first, to implement the big M method, we need to standardize the given LP, right? So first you need to modify the constraints of given LP so that the right-hand side of each constraint is non-negative. All right? And because there is no negative right-hand side, so we don't need to do that, right? And you need to identify each constraint with equality or greater than or equal sign, right? Because later on, we need to add artificial variable to each of these constraints. And then next, we need to convert the given inequality constraint to the equation equality constraint, right? So, like this case, both of constraints are greater than equal sign, so we need to subtract a surplus variable, right? And just to let you know that we are dealing with minimization problem rather than a maximization problem, right? So G is going to be 3x1 plus x2 subject to x1 minus 2x2, x1 plus x2. So subtract first surplus variable from the first constraint, z equals 2, subtract second surplus variable from the second constraint, and it becomes 3, right? And all of the variable x1, x2, and both surplus variable s1, s2 must be greater than or equal to, right? And then we need to add artificial variable for both of constraints, right? A1, let's say A2. And we need to add the corresponding non-negativity restriction. So A1 and A2 are both greater than or equal to, right? And let's say M represents the very big number, okay? It's a sufficiently big number. And if the given LP is minimization problem, you need to add M times A sub I, right, to the objective function. And if the given LP is maximization problem, then you need to subtract that value from the objective function, right? So because we are dealing with minimization problem, you need to add M times A1 and M times A2. Is that right? And based on this, we could construct an LP, Tableau. Okay? And now I'm going to use Excel spreadsheet like we did last time. Okay, first of all, let me construct the initial Tableau based on what you've done so far. Okay. So first column be the basic variables. And this next column is negative z, x1, x2, s1, s2, a1, a2, and right hand side, right? Is that big enough? Are you able to see? Okay. And the coefficient for the negative z column would be 1, 0, 0. And then x1 column would be 3, 1, 1. x2 column is 1, negative 2, and 1. s1 column is 0, negative 1, and 0. s2 column is 0, 0, negative 1, right? And a1 column is m, 1, 0. a2 column is m, 0, 1. Right hand side value z, 0, and 2, 3. Is that right? Okay, so this is it. And you remember, because the initial basic feasible solution does include the both artificial variables a1 and a2, which means both of these m value should be eliminated from the objective function row before you implement the simplex algorithm to solve this problem, right? So simply, we could do this like this. The first row, let's say R0 minus the second row and the third row becomes the new first row, okay, updated first row. So let me just copy this and paste it. And at this time, let me delete all of this, okay? So this value becomes the original row, row 0, right? Which is m minus this value, right? Minus this, right? So it's going to be m0 minus 1 minus 0, which becomes this m minus 1, right? How about this? It's going to be m minus 0 minus 1, right? So which is same as previous one, m minus 1, right? No, in that way we cannot delete m from the objective function row. I'm sorry. Yeah, we need to suppose to multiply by m, right? before you subtract it. So it's going to be R0 minus M times R1 minus M times R2, right? Becomes the new objective function rho. Sorry about that. So this should be 0, right? Because M minus M times 1 minus M times 0 becomes 0, right? Likewise, M minus M times 0 minus M times 1 becomes 0, right? What about this? This is going to be 0 minus 2 times M minus 3 times M, right? So it's going to be negative 5M, right? What about this? 0 minus M times 0 minus M times minus 1, right? It's going to be just M, right? What about this? This is same, right? What about this? 1 minus M times negative 2 minus M times 1. So this is going to be 1 plus M, right? Is that right? What about this? 3 minus M times 1 minus M times 1, which becomes 3 minus 2M, right? And this becomes just 1, right? There is no changes in the G column. Okay, now, based on this Tableau, which variables are basic variable? Should be negative G for the first column, first row, and second row, A1 is the basic variable, right? Oops. And second row should be A2, right? Is that right? I didn't make any mistakes so far, right? Okay, let me just double check it. Okay, so, okay, then let me ask you, is this optimal Tableau? We are dealing with minimization problem, right? Which means if there is any negative reduced cost, which means the current Tableau is not the optimum, right? Is there any negative values among this? This is the negative value, right? Which means x1 variable should be selected to enter the basis, the next iteration. And this row, this column, should be the pivot column, right? And based on this column, we need to do the minimum ratio test to select the living variable, right? This is the pivot column. And the minimum ratio test is 2/1 and 3/1, right? So minimum occurs at 2, right? Which means the artificial variable A1 will leave the basis as x1 variable enter the basis in the next iteration. And this is going to be the pivot cell, right? So in the next iteration, the x1 column should be 0, 1, 0, right? How would you make this from this using the pivot cell? The first row, well, actually, we don't need to do anything for this second row because we already have 1 down here, right? So we can just copy this value and paste it. Right? Then how do you make 0 down here from 1 using this? Just this value minus this becomes 0, right? So the last row, R2, minus the pivot row, R1, becomes the new R2, right? It's going to be this minus this. Oh. Let me do this again. So this value came from this value minus pivot cell, right? And let me make copy and paste it. Right? Okay. Then lastly, how do you make 0 down here from 3 minus 2m using the pivot value 1? So the first row, R0 minus 3 minus 2m times the first row, the pivot row becomes the objective function row, right? So that's going to be just 0. But what about this? Okay. Using the same formula, the x2 column would be 1 plus m minus 3 minus 2m times the first row, which is negative 2, right? So this is going to be 1 plus m minus plus 6, right? And minus 4m. Is that correct? 7 minus 3m. Is that correct? So I can just put it over here. 7 minus 3m, right? What about the coefficient for S1 variable in the objective function row? It's going to be m minus 3 minus 2m times negative 1, right? It's going to be m minus plus 3 minus 2m, right? It's going to be 3 minus m. So we can put 3 minus m in here, right? And the coefficient for the second, the S2 variable would be m, the same way. And what about z? Z is going to be, remains the same, because all these values are 0, right? These values are 0. And what about A1? A1 would be 2m minus 3. A2 would be 0. And what about the right-hand side? Let me do the right-hand side. It's going to be negative 5m minus 3 minus 2m times 2, right? So negative 5m minus 6 plus 4m, right? So that's the negative m minus 6, right? So right hand side value is negative m minus 6. Okay? And based on current Tableau, the basic variables are negative z, okay, and x1, right, and a2, right. So actually we could drop A1 column at this moment, right? Because it's going to be useless from this time. So let me put the very dark color on that. Okay? Okay, so is this the optimal? No, because these two values are still negative, right? So either of them, I mean the x2 or s1 can be selected to enter the basis, right? So let me choose x2 variable, okay, just arbitrarily. So x2 column becomes the pivot column. And definitely this bottom row would be the pivot row, right? Because only the positive substitution rates are used for minimum ratio test, right? This is going to be the pivot cell. Did I something wrong? Okay. So in the next iteration, x2 columns going to be 0, 0, 1, right? So first of all, the pivot cell should be 1, right? So it should be divided by 3. The bottom row, pivot row, well, this is the bottom row, right? Divided by 3 becomes the new bottom row, right? So this is going to be 3 divided by 3, right? And then paste it. Then how do you make 0 down here from negative 2 using the pivot cell? It's going to be the second row plus 2/3 times pivot row becomes new row number 1. Okay? So I'm going to use this formula for the second row. So let me type in Excel spreadsheet. Negative 2 plus 2/3 times pivot row, right, becomes 0. And paste the formula. Okay, and lastly, how do you make 0 down here from 7 minus 3m using this pivot value? the first row minus negative 3m plus 7 divided by 3 times the pivot row becomes new objective function row. Okay? It's a little bit complicated. So let me type in those formula. It's going to be because of the character m, I cannot directly use the formula. Instead, let me put the value. Okay, and if I apply the same formula to the S1 variable coefficient, then it's going to be negative 3m plus 7 and the coefficient for the S2 variable would be just m. And we don't need A1 column, right? What about A2 column? It's going to be 0. No, it's not 0, right? Okay. Well, at this moment, we don't need A2 column either, because we've learned A2 variable will leave the basis as X2 variable enter the basis, right? So we don't need to calculate A2 and A1 column at this moment. And Z value is going to be 0. X1 is 0. And I think I've got the wrong number. It should be 2/3. Should be number. Should be 7/3. Okay? And the right hand side is negative 25/3. I want you to double check all these numbers, the objective function row. Okay? And we still need to use this formula, right, to get those values. So, for example, if I want to get the right-hand side value for that, then it's going to be negative m minus 6 minus negative 3m plus 7 divided by 3 times the last row is 1, right? So that's going to be negative m minus 6 minus m plus 7/3, right? This is going to be negative m minus 6 plus m minus 7/3, right? So this is going to be removed. Negative 18 minus 7, 3, right? It's going to be 25, negative 3, right? Which becomes negative 8.3. Is that right? That's why we have current objective function value as negative or as 8.3 in here. Okay? Just negative 25/3. Okay, then this time the set of basic variable is negative z and x1, x2, right? And does this provide optimal solution? Yes, right? Because we don't have any negative numbers up here, right? So this is the optimal solution. And of course, in the optimal solution, both artificial variable has 0 value, right? Which means the original problem is not the infeasible solution, right? So the optimal solution is x1 equals 2.67, x2 equals 0.33, and the corresponding objective function value negative z equals negative 8.3, which means z equals 8.3, right? That's the optimal solution for our problem. Okay. Next, if you want to work with two-phase method, then the first 3 steps are exactly the same as we did in BigN method, right? Basically, we need to convert the given LP to the standard form by introducing either slack variable or surplus variable, right? And add the artificial variable to the same constraint that we've done for BigN method, right? So we need to make it to the standard form like this, subject to x1 minus 2x2 minus s1 plus a1 equals 2 x1 plus x2 minus s2 plus a2 becomes 3, right? And all the variables used, including the surplus variable and artificial variable, a1, a2s are all greater than or equals 0, right? And we need to find the basic solution which has both artificial variable, a1 equals a2 equals 0, right? So we need to introduce a new objective which is called phase 1 objective. Okay, that is minimize sum of all the artificial variables. Okay? So phase 1 objective will be added, the set equals W, the sum over all the artificial variable, right? And for now, we need to ignore the original objective function for a while, okay? And we need to solve an RP whose objective function is the phase 1 objective, okay? Which is W, minimize W equals A1 plus A2. And we can construct an initial Tableau based on this. Okay? Again, let me use this Excel spreadsheet for that. X1, X2, S1, S2, A1, A2, right hand side. Okay? think we need one more column, right, for negative z. Okay. And let's figure out this Tableau. Oh, I think we need another column, right, for negative w. And we need another row for negative w, right? So negative w column is going to be 1, 0, 0, 0. Negative z column would be 0, 1, 0, 0, right? x1 column is 0, 3, 1, 1. x2 column is 0, 1, 2, 1. S1 column is 0, 0, negative 1, 0. S2 column is 0, 0, 0, negative 1. A1 column is 1, 0, 1, 0, right? A2 column is 0, 0, 1, 0. Right hand side value is 0, 0, 2, 3, right? Is that correct? And again, oh, this should be 1, right? Okay. Again, we need to delete. Yes?
In column A2, I think number 1 is
Oh, yeah, you're right. Thank you. Should be 1, right? Okay. Any other errors?
And then x2 for the first version, that would be negative 2.
So negative 2? Oh, yeah, you're right. Thank you. Thank you. Is that correct then? Okay, thank you. Again, we need to eliminate those two ones from the objective function row, right? Because the initial basic feasible solutions does include both A1 variable and A2 variable, right? And simply we could do this by the first row minus third row minus fourth row. Okay? We need to do this calculation at the same time. Okay? So I said the first row minus the third row minus the last row becomes a new first row. Okay? So let's do this. Let me copy and paste it and delete all these values. Okay? And I said first row, this will be the first row minus third row minus fourth row. Right? Becomes 0. Let me copy that formula and paste it. Okay? So this is the initial Tableau for the two-phase method, right? As you can see here, we have the basis, which is negative W and negative Z and A1, A2. Is that correct? And because the phase 1 objective is to minimize W, right? Which means the current Tableau is not optimal yet, because the x1 variable has a negative reduced cost here, right? So increasing x1 variable will improve, which means will decrease the current objective function value. So x1 column is selected to enter the basis, right? So x1 column becomes the pivot column, right? And we need to do the minimum ratio test. Again, minimum occurs at the third row, which means A1 variable will leave the basis as X1 variable enter the basis. And this cell becomes the pivot cell, right? Okay, which means the next iteration, X1 column becomes 0, 0, 1, 0, right? So we already have 1 in here, which means we just need to copy that value. Okay? And paste it to all other values in the row. And we need to make 0 down here using the pivot cell. So the last row, R3 minus the pivot row becomes the new R3 row, right? And the second row, R1, becomes 0 by subtracting 3 times the pivot row. Okay? Becomes new R1 row. And lastly, the objective function row, the phase 1 objective function row, R0 becomes 0 by adding 2 times the objective, adding 2 times the pivot row. Okay? Becomes R0. So I'm going to put these formulas in Excel spreadsheet. Okay? So first row becomes this plus 2 times the pivot row. Likewise, second row becomes first row minus 3 times the pivot row. Okay? What about this last row? It's going to be last row minus the pivot row. Okay? So we can copy and paste it. Okay? So at this time, the basic variables, so negative W, negative Z, and X1, and A2, right? So is this the optimal Tableau? No. We still have 2 negative values, right? So either of them, either X2 or S1, either X2 or S1 can enter the basis in the next iteration. Okay? Let's arbitrarily select X2 to enter the basis. And we need to perform the minimum ratio test because only the positive substitution rates are going to be used for minimum ratio test, which means the bottom row will be the pivot row, right? That means A2 variable will leave the basis as X2 variable enter the basis, right? And this cell becomes the pivot cell. Okay, which means the next iteration X2 column becomes 0, 0, 0, and 1, right? So using the elementary row operation, we could make it. So first of all, the bottom row, R3, must be divided by 3, right? And the first row becomes 0 by adding the pivot row, okay? Which becomes R0. And the second row, R1, becomes 0 by subtracting 7/3 times the pivot row, okay? And the third row becomes 0 by adding 2/3 times the pivot row, okay? So I'm going to use this formula in Excel spreadsheet, okay? So first of all, we need to make this 1, right? It's going to be this divided by 3. How about the first row? It's going to be this plus pivot row, right? And second row would be this minus 7/3 times the pivot row. The third row becomes 0 by taking this plus 2/3 times pivot row, okay? So let me copy and paste it. So currently the basic variables are negative W, negative Z, and x1 and x2, right? Is this the optimal? Yes, right? Because we don't have any negative values in the objective function row, right? Except W and Z column, right? And currently the W value, the phase 1 objective function value is 0, right? And both artificial variables, so non-basic variable, which means both artificial variables has the value of 0, which means the given RP, is not infeasible, right? So what you need next is delete W row, okay? And artificial variable columns, okay? Like this. So the phase 2 RP is going to be reduced to this, right? 8.3, 2.7, 0.3. Is that correct? And the optimal solution for this phase 2 RP will provide the optimal solution for the original RP problem. Is that right? I think I've got the wrong numbers. Okay, let me just paste special. Okay, so let me take the values only. Okay, okay. Okay, so we are dealing with minimization problem. So is this optimal? Yes. We don't have any negative values here. Well, I'm sorry. Let me copy, paste it, and delete it. Okay? Because we don't need W column either, right? Okay. Because we don't have any negative reduced cost, which means this is the optimal Tableau for the original problem, right? This is unusual. Usually, after the phase 1 RP is done, usually we need to do several more iterations to reach the optimal value for the original problem. But right after we finish the phase 1 RP, we've got the phase 2 optimal solution, right away. The Z value is 8.3, and X1 is 2.7, X2 is 0.3. I think it's going to be the same as this, right? This is from the big M method, and this is from the phase 2 method, okay? Okay, then let's go back to the PowerPoint slide. Okay, like I said, let me give you another in-class exercise problem. So we will consider 10 simplex Tableau. And you are required to classify each Tableau if it is unique optimum, multiple optimum, unbounded, or invisible. Actually, we've done this before for the case of maximization problem, right? But again, we are dealing with minimization problem at this time, okay? And the first case would be the non-optimal, non-degenerate Tableau with bounded solution. Second case is non-optimal, degenerate Tableau with bounded solution. Third is unique optimum. Fourth is optimal Tableau with alternate optimum. And fifth, objective unbounded above. Well, it should be unbounded below, right? Okay. And the last case is Tableau with invisible basic solution. Okay. Okay. Let's take the first case. So what can you say about this Tableau? Is this optimal Tableau? No. Because we have two negative reduced costs, right? Let me use the highlight pen. Here, X3 variable and X8 variable has negative reduced cost, which means either of them, X3 or X8, should enter the basis, right? So once you select entering variable, what is the next step? We need to perform the minimum ratio test to select leaving variable, right? But here, if you look at the right-hand side, one of them is 0, right? One of the basic variable is 0, which means here X2 variable equals 0, right? Which is called degenerate solution. You remember that? So when this occurs, the next basis change may not result in an improvement in the objective function value, right? So this is B, right? Non-optimal. And degenerate Tableau with bounded solution. Is that correct? What about second case? Is this optimal? No. We still have one negative reduced cost, right? So x1 variable should be selected to enter the basis. Then is this the degenerate solution? No. All the basic variable has positive value, right? So this is A, right? Non-optimal, but non-degenerate Tableau with bounded solution. Is that correct? Okay, what about case 3? Is this optimal Tableau? Yes, because there is no reduced cost, right? There is no negative reduced cost, right? All these values are non-negative, right? So this is an optimal Tableau. And of course, this is not infeasible, right? Because all the right-hand side values are positive. This is not the infeasible. Then you need to decide if it's a unique optimum or a multiple optimum, right? Again, how do you know if it's a multiple optimum? If the reduced cost of any non-basic variable is 0, then we may say that we have alternate optimum, right? In this table, which variables are non-basic variable? x1, x3, x4, x7, and x8, right? And all the reduced cost for these variables, for these non-basic variables, it's a positive number, right? So this is the unique optimum, right? Which is C. Is that right? What about case 4? Is this optimal Tableau? No. We have two negative reduced cost, right? So either x3 or x4 variable should be selected to enter the basis, right? Okay, so in this case, if x3 variable is selected as a pivot column, then we are able to perform the minimum ratio test. Is that correct? However, if x4 variable is selected as a pivot column, we cannot perform the minimum ratio test, right? Because all these values are non-positive, right? So how would you conclude in this case? Is this unbounded below or non-optimal, non-degenerate Tableau with bounded solution? Let me give you a simple example for this. Let's consider this case. For example, maximize 2x1 plus x2 subject to x1 minus x2 less than 10 equals 10. 2x1 is less than equals 40. Both x1, x2 variables are greater than equals 0. Okay? In that case, we could make a simplex Tableau like this. Basis negative g, x1, x2, s1, s2, and the right hand side. Okay? Negative g would be 1, 0, 0. x1 column would be 2, 1, 2. x2 column would be positive 1, negative 1, 0. S1 column would be 0, 1, 0, 0, 0, 1. S2, right? Right hand side value is 0, 10, 40. Is that correct? And current basic variable would be negative g, S1, S2. Okay? Is that correct? So this is the same case, right? Because we are dealing with maximization problem. The current Tableau is not the optimum, right? Because we have two positive values, right? Which means either x1 or x2 can enter the basis, right? If you select x1, then you are able to perform the minimum ratio test, right? If you draw a diagram for this, it's obvious. It's 20. This is x1 minus x2 less than equals 10. And this is 2x1 less than equals 40. Right? Which means the feasible region would be this area. Okay? x2, x1, and 0. And the ISO value line would be something like this. Okay? So you can move either direction. Okay? But the objective function is maximize, which means we need to move ISO value line this direction, not this way, right? And definitely, this is the unbounded case, right? But here, the first case, if you select x1 to enter the basis, which means starting from the origin, you can increase x1 variable, right? So in that way, you are able to do the minimum ratio test, right? So that you can reach the adjacent corner point in the next iteration. However, if you select x2 variable to enter the basis, then you cannot perform the minimum ratio test, right? Which means you cannot reach to adjacent corner point in this direction. Okay? So how do you say? If you select x2 variable to enter the basis, then there is no leading variable, and x2 variable can be increased infinitely, right? Without violating any of the constraints. Without violating any constraints. Okay? Because if you look at here, each unit increase in x2 variable will increase current objective function value by 1 unit, right? So an infinite increase in x2 variable will lead to an infinite increase in the objective function value. So this problem has no bounded solution. Is that right? So if you go back to the case number 4. This is the unbounded below, right? So this is the case E. Is that correct? Because of this column, X4 column. How about the case number 5? Is this optimal Tableau? This is the minimization problem, right? Again. Yes, because there is no negative reduced cost, right? This is the optimal Tableau. And of course, this is not the infeasible case because all the right-hand side values are positive. And because we know that this is the optimal Tableau, next you need to decide whether it is unique optimum or multiple optimum, right? And how did you know that it is multiple optimum? Here, one of the non-basic variable, which is X7 in this case, has a zero reduced cost, right? Which tells us the increasing X7 variable from zero value, because X7 is the non-basic variable, which means it has the zero value. So increasing this X7 variable from zero will not affect on the current objective function value, right? So eventually we will have the same objective function value with different set of basic variables, right? Which means this is the case that the optimal Tableau with alternate or multiple or infinite number of optimal solutions. Okay? So this is the D. What about number 6? Is this optimal? Yes. We have no negative reduced cost, right? Okay. Again, since we know it is the optimal Tableau, we need to decide whether it is unique optimum or multiple optimum, right? Is this multiple optimum? Which variables are non-basic variable at this time? X1, X3, X4, X7, and X8, right? And two of them, I think, X3 variable and X8 variable has zero reduced cost, right? Which means either increasing X3 or X8 variable from zero will not affect on the current objective function value. So we will have the same objective function value with different set of basic variables. So again, this is D. Optimal Tableau with alternate optimum, right? Okay, what about case number 7? Is this optimal Tableau? No. X7 variable has negative reduced cost, right? So X7 must enter the basis, right? And then we need to do the minimum ratio test. To select living variable. But this is the degenerate case, right? Because one of the basic variable has zero value. Is that right? I said when this occurs, the next basis change may not result in an improvement in the objective function. Right? So this is the B. non-optimal and degenerate Tableau with bounded solution, right? What about case 8? Is this the optimal Tableau? No, because x3 variable has negative reduced cost, right? So x3 variable should enter the basis. And we are able to perform the minimum ratio test, right? So this is not the unbounded case, right? And is this the degenerate? No. All of the basic variable has positive value. So this is A, right? Non-optimal, non-degenerate Tableau with bounded solution. Is that right? Okay, what about the case 9? Is this optimal? Yes. All the reduced cost are positive value, right? So this is the optimal. However, one of the basic variable has a negative value. So how would you conclude this? Infeasible, right? So this is F, Tableau with infeasible basic solution. What about the last case? Is this optimal? No, because the x4 variable has negative reduced cost, right? So this is not the optimal Tableau. Then x4 variable should enter the basis, right? But we are not able to do the minimum ratio test, right? So this is the unbounded case, right? So the answer is E, objective, unbounded, below. Is that right? Isn't it easy? So you are able to answer this type of questions in the exam? Okay? Okay, I think that's all for today, and I will see you next time. Thank you very much.